Thank you everyone for joining today. I'm Stephan Sahm and we are doing a standard Fall in Love with Julia session, this time focusing on streaming analytics. It's one of my favorite topics because it really can showcase the speed of Julia in one of these applied settings. Streaming analytics is useful for almost any company out there. And so I really like this use case. And we also have an awesome package around the site, OnlineStats, which I'm going to introduce to you today. And you will see it's full featured. There's a lot in it already. And it also makes a lot of fun. Simple interface, works, and yeah, you can also use it for visualization. So this is really just a nice tool to have in your tool set. So I prepared the link. I've shared it with you in the chat already. And by clicking on it, that's not the image, you will get a Jupyter instance as always. So you first see a binder window like this, which is loading the Docker file that's luckily cached. So as you see for me, I just clicked link and kind of 15 seconds later, I get a fresh Jupyter Notebook instance. So I hope the experience is similarly well for you so that you also have direct access to this interactive environment. Everyone has their own interactive environment. So yeah, if you change something, there's no fear that you interfere with someone else. But this is really your instance. You can play with it. At the top, as already said, there's this launch binder button. In case things break down, you can click on it to restart the same notebook in a new instance to get back to a live session. Okay, great. Yeah, so to start with, there's very big news I would like to share with you. So you're, in the sense, a very special guests today. I myself am so eager into Julia that I started my own company called Julia Performance. And yeah, this is going to kick off like the last 2 months. And I'm looking forward to seeing it grow over the next year. With the sole focus on Julia, I really hope to bring Julia to industry and make it a valid alternative to Python and R and all the others. So my new slogan is making Julia the standard, and I'm looking forward to also do this with you. So thank you for also joining always Julia User Group Munich, and sharing the passion. Thank you very much. One big thing also to note is that with this, I also now create a YouTube channel, and where all the recordings are stored. So this is in the sense also big news. So if you go to YouTube and look for the Julia Performance, then you will get actually, you need to write it together. So then it will be there. So there's the new Julia Performance channel. So also bound to this new company, but a place where we have full control over. So that's the big thing. And all the videos which we have been recording from the last sessions are there online. So enjoy also if you want to relook something. And this will also be the place where from now on everything will be uploaded kind of straight away so that the recording is available. I'm very happy that this is finally in place and we have like a standard upload pipeline. Yeah. Great. I share the link. Let me put it also here. So this is the YouTube channel. Okay, great. So let's take a look then at OnlineStats. OnlineStats kind of the go-to package for doing real-time processes with also already a mathematical approach, some machine learning in there, some statistics. So it really fits quite well into the Julia ecosystem at whole, which focuses on data science. But brings this now really to the streaming application. They have a nice logo, also a nice GitHub page. So give them a star. It's really a nice package. And they describe themselves as online algorithms for statistics, models, and big data visualizations. Key features, high performance, and the single path algorithms. These are kind of the key thing. They go one time over the data and are ready. So this is kind of the setting you need for streaming, because the data arrives and is away. So you need to do everything you need to do on this one pass. And yeah, and the way everything is implemented is that actually you will see the interface yourself. You update all the models once at a time. And this guarantees you then also that you have actually an O of one memory. Yeah, so this is all kind of the basics. So you can use it for streaming and big data even. We will also see the big data part a little bit. Okay, so what we'll go over today, I have two basics parts and then one going into visualizations. I hope this one is going to work. So the visualizations seem to be quite heavy. I downscaled them a little bit to work with Binder, but still I hope that they will work. Let's see. So in case there's some hacking, something is a bit slower than usual, then you need to skip the visualizations part. But I think they will work also with this Binder instance. Then I'm going to streaming and big data, and last a section about the machine learning, that you see that there even is already support for more advanced models. Okay, so first line here to execute. So in Jupyter Notebook, I'm myself using keyboard shortcuts, Shift and Enter. It's going to execute a cell and moves the focus down to the next cell. You also have here the run button. This is also running a cell. And yeah, you have kind of a bit more control. Enter is going to evaluate and stay in the cell. But yeah, so in principle, Shift and Enter is the one which I'm using all the time, but the GUI works also always. So that was quite fixed and quite fast. So we loaded a couple of standard packages, and thanks to this Docker image behind the scene being pre-compiled, this is by now really fast. So I'm happy about the speed of this loading. And so let's directly go into OnlineStats. You import it again with using. That's kind of most convenient in this setting because it makes available all the different commands from OnlineStats. And if you would type import, you always would have to prefix everything with the package name. So that kind of from a practical usage, the difference between these two import statements. And so now we somehow have to know which one belongs to which package, but usually we will manage this. So the mean is now from the OnlineStats package. And this is the way you create it. So there's a default, some default arguments here, which are actually used. So, and the point, or the main point, which what's here kind of a default, is going to be seen if we look at the types. We've namely created a mean of a special type of a float 64 and with a equal weight weighting. So there are some extras which are already here by default. And we take a look into the equal weights a bit later on. And yeah, and so the super types here, you see there's the comma. So this mean type is a subtype of the OnlineStat type. And this is then parameterized by another type here, number, also defaulting. And then this thing, of course, is everything in Julia is subtype of any. So it might be a bit theoretical to start with, but this is kind of really the foundation of everything else. They all follow this same line, that they have the type of this observation. So how it's described here, stats are always subtypes of this type, where this parameter describes the type of the single observation. So this standard mean is really for getting the average of floating point numbers or numbers in general. So that's kind of the restriction, and we cannot easily take a mean of strings, for example. I mean, this makes sense, but this is kind of also baked into the type system for performance reasons. So having this now on the type level just gives us a lot of extra information to speed up things. Okay, so from a usage point, this is often more or less hidden. Sometimes you have to explicitly state the type, but usually you know it. And yeah, we will see kind of a couple of situations where this also gets in the way, but also a workaround. But yeah, maybe to remember at this type, so this was done intentionally and mainly for performance reasons, so that the compiler really knows a lot. By having one of these so-called online stats, we can create some random numbers and fit our little aggregation. Yeah, so I've wrote here a little for loop. Actually, now I remember, so maybe this is actually a bit better. So I'm zooming a bit in, hoping to have a better view. So just looping over our data, we call the fit exclamation mark function, which is going to change our aggregator, our online stat. And we can print it meanwhile and see that it's changing. So that's nice to see. And we can grab the final value of our aggregator by the value function and yeah, and get this aggregation out. So that's kind of the very basic algorithm you'll use a lot. And just to see it a second time, you can directly pass an array. So, okay, so the connection failed for me. So I hope it's not. So I myself have to reconnect. So the second example here with the wise2 creates again some random numbers and calculates the mean by now passing all these numbers at once. So this is kind of the second type of use. Instead of providing it value by value, there's a convenience version where you can directly pass an array and it will iterate over it. So this actually uses the iterate interface behind the scene. And yeah, and with this then uses iterate next, and goes through everything and fits it on there. So I'm back here. Okay. So yeah, so you see that everything, I just close the other one. It's nice, and just for an alternative part, you have also access to fields. So this mean aggregator, if you type dot, and for me it's the tab character, I need to press it twice in case. There's the number of instances, number of observations, the weight, and the mu, which is the mean itself. So this is another way of accessing it, but the value function would be the interface. Okay, so the last standard function is that these aggregators, these online stats, can be merged. So we now had one with an average of 5, another with an average of 0. We merged these, and they also had, luckily, the same number of instances. So the mean is indeed around 2.5. Okay, so that's the very basic, and I would like to give the state to you if you haven't done it already here. So there are a lot of other online stats aggregators, as I would call them too, and you can just seamlessly apply them. So I opened here a little cell for you. Please just create some random numbers or reuse the y's, which we've been using above, and call the fit function on your own to see that there are also others. So one example would be variance, but there are many more. So take a look here at the links I've listed, and yeah, give it a try. Okay, so I'm this also, so to to start, the univariate statistics are definitely the simplest. So they are here in the online stats auto-documented. We see the mean, the variance, with quantile versions. We have extrema, momentums, some geometric mean. So yeah, pick the one you want. I go with extrema for now. So I make a new extrema. They called it now O for online stats. And yeah, now you need to fit whatever you've chosen. And you also need to choose on what you want to fit it. So let me create some new random numbers. Okay. So, and finally, I output the extrema in this cell again. I think this is even not needed. Let's take a look. This fit returns the online stat itself. Okay, so fitting this extrema on these numbers already produces a minimum value with more than 5 and 8, and for sure, because this is a normal distribution, if we would increase the value, yeah, our min and max rises. Okay, so I hope you also experimented with one or the other and see that they are really all working the same. So this is a super simple basic interface, and yeah, gives you access to all these power. It's impressive that you can combine all them in the same interface. I took 2 other examples here, which are especially interesting. The one, sometimes you really hope to have something like this, is called hyperlog, quite complex name. And what it does is to calculate the unique number of elements. So yeah, that's a typically hard task for streaming process, because in case you have multiple number of elements, you, oh, whoa, okay, so I get a quick destroy. Okay, so I hope your kernel is at least a little bit more stable than mine today, but it seems at least that it may be that the resources are bound to fewer time. It was about 15 minutes before, but yeah, seems to go down. Okay, so the hyperlog counts the unique elements, and this is quite hard because to know whether an element was already there or not, you usually need to store it. And storing the elements is then, in case, almost as big as the set itself. So no way you can do this in a streaming fashion. It will blow your memory very, very quickly. So there have been a couple of ideas to do this more efficiently, but then approximately. And the hyperlog is one of them. And if you run them, you will see that it actually outputs a continuous number, which yeah is only an approximation. But yeah, it's still nice to see that it doesn't approximate a constant number, but the algorithm is just continuous. This can be really, really useful. So just good to have in mind that something like this exists, so that you can really count your unique elements over super large sets without fearing of exploding your memory. So I now jumped in there, and it just computes. So yeah, and I have another one here, which is the histogram, where we have to pass in as an input the bins which we want to count. So a very simple one, and again some random data. So we have in the statistics package of Julia, we have a couple of extra statistics we can use, like quantile and median, and also the extrema. So these are pure Julia functions, not from online stats, but we can use them. And yeah, you see kind of that you can approximate with this just the distribution. So it's the standard non-parametric density estimation you have available, and you can readily use it. You will see that it also has nice plotting support a bit later on. Okay, so this was first basic part. Paolo, thanks for giving me the feedback that you also keep getting disconnected. So I fear that for today, it's going to be the way we have to work, but I will check that this may be improved for the future. I'm I'm not sure because we've been using Binder every time, and it's the first time it disconnects so quickly. Thanks CM for questions. So Binder was the last 10 times stable, and yeah, very stable. So this is the first time. Let's see. I mean, it also costs something. Maybe they reduced the funding. I don't know. But usually it's much more stable. But of course, as always, you can also make a local Jupyter install. But yeah, this is just more involved. So yeah, the GitHub page is completely self-contained. So just for those interested, of course, you can copy the repository, instantiate it with your local Julia, and then yeah, open the notebook in iJulia. Okay, so I'm going back to the basics part 2, and here we speak about how to combine these different online stats, these different aggregators. And there are 2 principal ways to combine them. The one is called series, where we just apply multiple of these online stats to the very same time series. So data comes in, we just compute both stats on the same data. There's an alternative, the group, and this one, yeah, as the graphic really nicely depicts it, expects kind of also a group of incoming data, which is then split to the single online stats. Okay, so they are very easily created. They have just the name, like they are in the picture. So series is combined by different basic online stats. Yeah, and you can again call fit on it, and the fit will be passed forward to the underlying online stats. So very, very simple. Same goes for group. So we again combine a couple of online stats. So here there's now a new interesting one. There's a count map, also very useful. And the input also now needs to be manipulated. So we use the zip function, which is the standard function of having kind of 2 different arrays or iterators put together so that we have these pairs like they are depicted in the graphics. So yeah, this we have to live with that. I need to reconnect. So what's actually faster than usual is the reconnect. So I'm very surprised that it's kind of below 15 seconds. Sometimes it took kind of a minute, which is still fine. But yeah, so at least they improved the startup time. Let's see. Okay, so this is the group part, and there's a special group. So again, so like this is the one key message today. Yeah, there's this fit function, and this does almost everything. So you again can fit this grouped aggregator on the data, and it will propagate the fit to all its subparts. There's a special group by, which automatically grabs the groups from the data. So we have here, for example, X and Y. We also have to zip the data. So this is the same like for the group. And the group by just now, has instead of these 2 different, these 2 different aggregators. The first is now just the type, what should be grouped. So in our case, we have a Boolean group by variable, and could be, of course, something different. And this is then the normal aggregator, which is run. So I'm jumping back. So you always need to execute kind of the first 2 cells. The online stats are important. Okay, let's see the group and the group by. So the next very generic and flexible tool is filter transform. So I just computed. So you see that the group is also nicely depicted. So you have the group looking like a little tree with the mean and count map below, where you see all the collect stats. And with the group by, it's similar. On the first level, we now have our variable, and in our case, our Boolean variable, which is split up into all the values. And then below that, we have our online stat, which in our case was series, so combining two different stats. So this is no problem at all and just works. Okay, nice. Filter transform. So yeah, often in streaming processes, you not only want to aggregate, but you also want to transform something, compute something on the fly, and also filter out some mistakes. And one of the most typical filter operations is the missing filter. And there's some specific online stats here that needs to be imported individually. And then we can wrap our online stat, our stat, into the skip missing. And yeah, magically it will be able to deal with the missing. And you can really imagine this again, like going nested, going a layer down. We start the fit, calls the fit function on the skip missing, and this will filter out the missing and forward the fit function onto the inner online stat, which then will see its normal values. So this is really very intuitive how it works. And thanks to Julia, this also works efficiently and performant. Okay, so the generic version of this is called filter transform, where you need to specify, again, the type. Here it's a little bit more complex. So we have this missing, and the number is kind of, this would be a more complex version of skip missing. And we can specify a filter. For example, we filter on is missing. This is a special support. So the exclamation mark, as you know, is usually the not. And a couple of functions are specifically supported. So is missing has a support for this operator and gets the upside down. And we have a transform function. In this case, we use the absolute value of something. And again, we can put this this little series on top of some data and see that it works. This is the very flexible one. And because in real life you have to do a lot of these transformations, they also support a special syntax so that you can write like a pipeline. So this is just the very first time I have to reconnect twice. So it might have happened that beforehand I reconnected one time in a session because of something, but yeah, so this is really new. Okay. So this syntax here with the pairing operator in Julia. So this is really just having first value and the second value and putting them together into a pair where they are both. And this can be changed to have kind of a nested pair. And yeah, it just has special support in this filter transform function. So you start with a input type of string, then you, in this case, apply a filter, so a function which returns a Boolean. And then you apply a transform function, and then finally you apply, in the sense, the other aggregator. So I like this quite a lot because it really goes from input to output, so that also the place of this input type and the other inner aggregator feels very intuitive. So you can simply use it there. Yeah, so it will, I just made up this little example there, having a string and splitting it up. So we filter on things that have a minus and just parse it to int and then call the mean and variance. So really just little dummy example, but you see the flexibility of it. Okay, filter transform needs to be imported, of course. So with this you can build a lot. Let's try catch as a final of these bonds. So in case you're not sure whether your code rises some errors, this is actually a nice way to make it safe. And especially for streaming jobs, this can be very, very important because if there's an error, you usually don't want the whole system to shut down because of a single error. So that can make a lot of sense to just log the error away and see what is going on. And then, yeah, in a more offset setting, look how you can fix it, but not that your whole system just shuts down because a special case kicks in. So this is cool, a try-catch, where you get the errors which are collected. Of course, you can also put this into a dashboard or something. So yeah, no problem with that. And then under stat, you have the inner stat. Nice little tool. Okay, last part of this basic part 2 is about weights. We've seen them in the beginning already, that this is part of this of every online stat, and you get automatically a default weight. And here's a nice little GIF from OnlineStats where they compared different weights. So we've seen in dots all the data, and we have this equal weight. Remember, this was actually the default weight. So all points are weighted equal. We have the exponential weight. So a new point gets always the weight of 10% in this case, 0.1. There are others. There's learning rate, where the influence of new points gets down. Yeah, there's harmonic weight, Mac-Klein weight. There's a lot. And you can, of course, also define your own weights. So this is all for dealing with the change in your data. And depending on your case, it might make sense to use the one or the other weighting. So let's see it concretely, how to change this. So we have, again, some example data. And fitting now, we can fit a special mean where we specify the weight by a named argument. And there are a lot of weights which are already there. So we have, for example, the exponential weight available in our setting, and we can call it there. So yeah, and there's another way. Next to these pre-built weights, we can also specify just a function, and it gets the input value. So this is actually this x is the number of observations. So actually could be named n-obs, and given the current number of observations, we output the weight of the current. And yeah, and then we can fit it again. There's an alternative, the equal weight. And yeah, so the equal weight is like the default, and it will weight all the different data points equal. So yeah, there's no bias towards new data or old data. And yeah, my little exercise here to you is to actually give it a try and think about which function this actually would be. So there's actually a very nice solution to this. This is very simple, but yeah, it just takes a little thinking. So you can define the equal weight also with such a function, and yeah, and try it out. What could it be? And see that it's really nothing fancy, but yeah, very basic components which just seamlessly work together. As you've seen, I'm disconnected and need to reconnect again. So yeah. So you can also play with this weighting a little bit. Yeah, the standard imports. I take my random wise. I have this little template here. As you can imagine, if you use another constant, then yeah, we are still in this exponential weight. So this is not going to work. We somehow need to get away from the constant. And yeah, I see a good solution, kind of the solution. Thank you, Frank, for posting. So if you don't want to see the solution, don't look into the chat, but I think we we anyhow can go forward. So actually, yeah, the solution is right, that we just take the inverse of the current number of observations. And yeah, so this makes intuitive sense that everything is just weighted by the number of observations. But so what can confuse you a little bit is that this is, of course, an update mechanism. Yeah? Having this exponential weight in mind, it says how much we weight the new incoming data point. But still, this works out. So if you write this recursively, or this was super quick. If you write this recursively, yeah, so every new observation gets the weight of 1 over the total number, yeah, and the rest, of course, 1 minus this. It actually turns out very well that everything has the equal number of weights. So it's just a really nice little thing. And in Julia, you can even kind of make this a 3-character version. You can put the inverse function in here, and it's super condensed. So it's very impressive that you can write this standard just as this inverse. Yeah, little gadget. And also thank you, Frank, for posting the solution. It's always, yeah, I'm glad people try it out. Okay, so this was the basics. Thank you a lot for doing it with me together. And now I come to the visualizations part then. Of course, if there are some further questions, please always feel free to raise them. Yeah. So we have resources, time for that. And I also like to answer questions. The visualizations part is now just to give you a feeling that you can really use OnlineStats for getting a feeling of your data. So the first visualization I want to show you is just a trace. It's super, super simple. And as you see, there's another little exercise for you right below because it's so simple that, yeah, you can use it a lot. So what this does is that it just stores the history of your training process, if you want. Yeah, you have your online stat, your aggregator, and it learns step by step, as we know from the data. So you can also take a look at actually how it learned. And the trace now stores this in the background so that you can easily plot it. So you see we have also nice support. We can just call plot on it. Yeah, so we have built up a trace with extremer, and we see that here an obs is always the number of observations. Yeah, with more observations, our extremer get larger. That's, yeah, what we expect actually, because the more we see, we can also see the unlikely extremers left and right. Okay, so this little exercise here is to showcase you that you can use this also to combine a lot of other things. Yeah, so we can just build, of course, another. Oh, yeah, I dropped the fit. You need, of course, to fit it. You can print, of course, a mean and everything you want, yeah, and it will have its default plotting style. So you can also plot a variance. So this is all easily possible. And what's nice, so maybe some of you already found this out. So we just learned about the series a bit above. And yeah, you can actually combine this very nicely into a trace of multiple. And then, yeah, it will just plot them over another. So I like this very much, that you have super flexible plotting utilities. So if you build your own aggregator, yeah, we have, what was it? You can probably take the median, and okay, median was not harmonic mean, geometric mean maybe. To look into the documentation, so you can, and in case something does not exist as a classical online stat, you can of course also build your own online stat. But yeah, so this nice simple plotting. Going to next very useful one is just histograms. Executing this line will show you that there are actually a couple of options if it comes to histograms. We've seen the simple hist already above, but there are different versions of how you can compute a histogram. So k-hist is another version. It's a little bit similar from the naming to k-means. So yeah, the algorithm is like finding centroids. The standard histogram, we have an expanding hist, and we have also a very special ASH operator. So I want to point you just to the documentation respectively. As a remembering, you can always use the question mark before something and then your name, and you will get the standard Julia help from it. And in this case, the expanding hist operator is actually really, really nicely explained, even with an example of how the algorithm works and how you can imagine this. So you see also the results are quite different. Yeah, so yeah, the density estimation of the ASH combined with an expanding hist is really very, very nice, while the k-hist with at least 25 centroids is a little bit unfortunate here. So it's of course random, but still, yeah. So you have a couple of options here. And now I would like to go to the 2D case then. So this was just a histogram of a single. And yeah, so sorry, yeah, there's a summarizing 2D. OnlineStats gives you also a lot of help for plotting and analyzing 2D data. So let's take a look what we have here. So we have y-axis, we have a lot of random numbers where we sum them up firsthand, and then we add another random numbers on top of it to scale them. Okay, let's wait for the plot. So what have I printed above the plot? So this is 2D, and whoa, okay, so I have connection failed. Okay, so if this was kind of an immediate fail. Let's see. So if this really doesn't work out, I will switch to my local Jupyter instance. Yeah, but then of course it's a pity that you yourself cannot easily replicate it here. Okay, I will spawn up local setting. Wow, Simon, thank you very much for the hint. Okay. Yeah, I can open the file seamlessly in my local Jupyter instance. But this can definitely be a reason. Thank you for inspecting it. So I have the fit now here on the binder instance. here. So this is a little example. So we have it here. I will also compute the next one. So the partition is really nicely seen in this picture. So this partition function is super mighty. It just cuts your time series into different bins and computes your aggregator on top of it. So you can have like a 2D view summarizing your data. So it's for continuous or categorical data. Here in this first example, there's continuous data where we use a histogram to print it. And in each partition, you can control the number of partition. I've set it to 50. To downside it a bit, standard is 100, the default parameter. And yeah, the more resources you have, you can increase respectively. And having the Plotly backend, it's also really nice to have it inspectable. So I like this very much. So you can zoom in into a little field and just inspect your data more interactively. So this is it's like a good standard. And yeah, we can apply the same to other aggregators. So here we just combine the mean and the extremer and have it also been plotted partition-wise so that we can see how our data evolves over time. And yeah, the same works also with categorical data. So here we have just a count map, but the general idea is totally similar. So we again cut our timeline into different partitions, and then we compute our aggregator on this partition. And the nice thing about this is that the plotting is really well supported, so that we can just take a look at this. So if I constructed kind of a couple of little strings, so our categories, which change over time, but just having them stacked into another. And and you can see this nicely also in the plot. Yeah, so there's another version of this called indexed partition. And this was it. Okay, so a little bit short. Let's take a look at this link here. So if you're here, you can just also click on online stats index partitions. So we will jump into the documentation of Binder of online stats. So being here, I will just put the link also in the chat. So here we are. I took a couple of things from here, just reordered them a little bit. So, but the index partition can also be seen here quite nicely. So what you now have is that you again have two-dimensional data, so X and Y. And you zip them together like for the group and have now an index partition, which looks very similar to our other partition, but takes into account this X dimension for splitting up the data into partitions, so that you finally then see a summary, which is really just the 2D data. So that's nice. As you see, of course, it always has these cuts in between where the partition boundary is, but this gives it an awesome flexibility to really visualize whatever data you have. So I like this visualization style quite a lot. And so there's also a version, extra support for dates, because we are always speaking about time series. So that's also a nice example. There's another version of it, and and the last visualization, I think, or not the almost last visualization is that there's also a mosaic. I haven't put the link here. It's called mosaic, and this is kind of for 2D categorical data. There's also here, that took this example also from the online stats documentation. Nice little side note, there's an R datasets package where you can access the standard analysis packages from R. So here we just load the diamonds package, the ggplot2, and to take the cut of diamonds and the color of the diamonds as two categorical variables and aggregate them with a mosaic. And yeah, this gives us just a nice, it's called a mosaic plot. So yeah, a good summary of how the data is distributed. And then finally, for this visualization set, there's a little example I got where we built an animation. So we use a GIF macro, which comes from plots, from the standard plot package. And we then kind of iteratively can look at how our aggregator performs, how our aggregator evolves. And here we use a heat map aggregator, which is in the sense also fitting to the others, like a 2D aggregator where we have continuous and times continuous data. And yeah, it's quite, there's as stated in the comment, it is simpler, or there seems to be a bug in the Plotly.js backend. I need to switch to the GR. This is the standard backend for plots, and then everything works. I myself like Plotly.js very, very much for this interactivity. Of course, the GIF is not interactive, so yeah, this may actually be the reason. Yeah, so hence I'm switching back here. Okay, so I think I'm currently loading the dataset. Yeah, so this took the time, and here's the mosaic data. So we see it with the different colors. We have as legend the one categorical variable, and on the x-axis the other one. Yeah, so if you have this data category times categorical, you can use this aggregator and the plotting to visualize it. Whew, okay, so quite an unfortunate unstable connection. I'm switching to local Jupyter Notebook now, just to simplify my life here. To give you a little bit better experience, and you can at least follow me here. Okay. So making it a bit bigger. Okay, so I hope you can again see my screen. Sorry for the inconvenience of the binder system working so badly today evening. I'm now in local mode. Yeah, we went through the visualizations. So I hope you got the feeling that this online stats gives you a lot of available aggregators, which are also supported by the standard plot function, so that you can, in very, very quick manner, get a feeling of your data. And all this is using this underlying fit function. So everything is very simple. It goes through this one step by one step algorithm and updates itself. So it's really also a very flexible setup, and you can extend it to your specific needs, build your specific aggregators. Yeah, so easy to use, comes battery included, and hackable to the ground. Okay, so now I would like to bring you to the streaming part. We've seen now the standard set of tools which are available, minus the machine learning part. I've saved this for the end. Now I would like to show you how you would actually apply this in a real life scenario, and with the example of a CSV file. So this is a Kaggle competition. Kaggle competition data, and actually this Binder notebook, I enabled it to download the Kaggle data. Was not so simple, but yeah. So in case the Binder is stable for you, please feel welcome to try this out. So this will download the Kaggle data, and the second run will unzip it into the data folder. I've done this already. So I can see the data here, and you can also see how large the data is. So what we're going to look at is this little training CSV, which is about 5 gigabytes in size. So usually almost every standard machine is going to collapse under such load, because then in best case you only have to load it once into memory, but often your algorithms are not that optimized, so you load at least twice or 3 times or even more. So memory explodes super easily on such a scale. And Binder notebooks anyway, they have 2 gigabytes of memory, but this would be enough for us. So I'm loading the CSV library, which has a lot of features and also nice for node streaming applications, but it has also special support for streaming applications. And this is a special constructor called csv.rows. One of the standard ways to construct a CSV, and this one is really focusing on giving you an optimal streaming experience. So this is super nice, and we can take a look at this, for example. So I'm using another special function here. It's called the benchmark time, btime, a function from the benchmark tools package. I've loaded this already in the standards above. So this would be the package name, just to let you see it. Nice little function to see how much memory we also have allocated. So just for comparison reasons, I limited this whole thing now to a couple of rows. So as you can imagine, 5 gigabytes, there are many rows in there. And this would be one way to just use standard Julia. So what I'm now doing here is to sum the number of rows. So if this is true, then we should have the same number here. And we just have an inner iterator, which is then put into the sum. And this, I also like this because you can see that this really already optimal in performance. So it's really relatively quick. And so we see that we are in milliseconds reach, and we have almost no significant allocation. So we went through this whole CSV file without actually reading it. So this is super awesome. The CSV rows is unbelievably optimized. So we haven't loaded almost any data into memory. So everything is kind of pointing to the correct data, but because we haven't used the data, we haven't loaded anything actually. So this is just from performance perspective, awesome. There's the OnlineStats alternative to this. So this was kind of plain Julia, and there's also an aggregator just called Counter. And there's it also, so this was one place where I've stumbled upon this element type. So like others, it also needs to be initialized with the element type. I'm now looking through the CSV rows. So the default, so if you would leave this out, it would get number as default, which just is not the correct type. And so this one is it. And you also, so we can do this the same. And I also let this run. It takes again a little bit time, but as you see, we are in the milliseconds range. So our benchmark time is actually now taking this extra amount, which we currently wait, just for assessing the allocations and everything, and giving this kind of a certain number. So we see that the counts, I haven't highlighted this. Now this is of course the correct number of counts. And again, we see also very few allocations, and compare these two numbers. They are really kind of identical. So our plain Julia solution is kind of exactly as fast as our OnlineStats implementation. So if you will, in this concrete example, our online stats implementation is even a little bit better. So this goes both ways. Yeah. So this is really also a nice implementation of the online stats. In the next cell, I'm now switching out the rows with the csv.file to give you a feeling what it would be like if your system does not support this iteration row by row style. And this would be what file gives you. And we can also just count over this different kind of reading the data. And you will see that our memory allocation is much larger. And probably also we need more time, but let's see. And then in the next two cells, I've prepared just a little bit more complex example to not count, but take the mean of some concrete. Yeah, so you see we are now in seconds. So it's like 3 times as slow. And what is really decisive is the memory allocation. Yeah, so now we have read data into memory. So of course, if you want to look into data, you need to read the data. But for an example, like taking a count and counting things is really a typical operations. So yeah, you want to have a way where you don't allocate all this data, but just can do the count as quickly as possible with the least amount of memory. So this is kind of the bad way to do it. And the same holds also for other aggregations, of course. So this is now here a little detail also how this interface works. So if you take a look in more detail, I'm now constructing then another iterator from my rows. What I do for every row in my rows, I read out my the number of passengers. So I haven't introduced this data set, I'm sorry, but it's about taxi drivers. And there's information about how many passengers are there, and also how expensive the drive was. Yeah, and this is kind of information we look at here. Of course, only example information. Yeah, and you see that in both ways we have kind of a different access. So for the super fast row-wise version, we actually need to pass the strings ourselves. So we call the pass function so that we get a real number out of the input string. If we use the file, this is more convenient. We already get it passed. The Csv File Constructor reads the whole data into memory, so it already can infer the types of all the columns and bring the data into the types for your convenience. So this is nice. Of course, a nice feature, but it's similarly awesome that the CSV package of Julia also gives you access to this lower level, this lower level API. Okay, so what do we see here? So we have again a difference in memory allocation. So here in this little mean example, we really look at the data, and the count we don't need to look at the data at all. So we've seen that actually with kilobytes we haven't read any data. So now with the mean we actually read data, but it's much less. Yeah, so this is kind of the key knowledge, and this is going to be constant now. While if we increase the size here, we will of course increase also the size of our CSV in memory. Yeah, so I like this, that we can actually take a look at this concretely thanks to the benchmark timing. Really lovely little tool. I'm using it a lot here and there. So yeah, nice. Okay, so I have here a little other task for you. I guess this one is now getting more and more difficult the further down we get because of the reconnection. But I see also that there's a question. Thank you, Matthias, for asking. What if you add weights to the mean function? Okay, so I take this just as an example for running another online stat over the file. So I take the rows version here and try it out. So we have here, we can set the weights and we can use just an exponential function, for example. So what would be the expectation? So we get, of course, another another aggregation. We aggregate the numbers differently. So let's take a look actually what have we calculated. So with all our taxi drivers, there are on average 1.7 passengers on a taxi drive. Okay, so yeah, that's, I think, good. More would be even better. Then the taxi is better used. But I would have expected actually a lower number, so that there are so many people take a taxi on their own that it's more towards 1. So I'm a little bit happy that it's not near to 1. Okay, so if we weight this differently, of course we get so the B time was good for taking a look at the actual allocations, but of course it takes some extra time. So to just speed things up, we don't need this. Yeah, so if we value later instances higher in this regard, we get actually a larger value, but this is definitely by random. Yeah, but I guess your question, Matthias, was also that this affects performance. So I don't see, I think it's very similar. So the nice thing about Julia is that adding custom parts is really not affecting the performance side of things. So this feels already very intuitive to me. And yeah, and as we can see also, it's in this sense, it's already faster. So we have a little bit less time to spend, and the allocations are completely identical. Makes sense. Yeah. So this might be in the sense, just a good remark that in Julia we have the luxury that everything is optimized and has the nice Julia performance by default. So we can just customize our things. Okay, thanks for the feedback. It's really valuable to have your feedback on the chat when my screen freezes. So I'm also glad it's back. Yeah, so what I've done is here I set up this little mean with another weight. We can also put a variance on it and calculate the variance. So this is all easily done. And to have a nice little example, kind of a little bit more complex, I'm now doing a group by here. So the last very aggregation for the streaming part. Okay, so we have a variance of 2, also interesting. Not super high. Yeah, probably expected. Yeah, it could be that there are some really extremes in there, which are just buggy data. Have put it just far higher. Okay, so we again read all the data. Now I'll read all the data just for a final example. And I get the passenger count again. I convert it to string. That's an interesting implementation detail here, because if we take a look actually at the rows, let me do this here. This is just an iterator. We can, because it's an iterator, we can also grab the first row of it. And yeah, and there's a very special support. So we haven't seen this before. So the CSV also gives us information about what is actually in the CSV. That's really nice. Table schema to see this here. Lovely support. And if we get the first row, just as an example, we see that there's actually a special string format used. And this is not a standard string. So I'll convert this here explicitly to a standard string. And it's just nice to see. This is for performance reasons. So this string is not actually copied, evaluated, but it just points to the big CSV. And yeah, if we take a look at it, it reads it from this central storage. So this saves us all these allocations above. This is one of the optimizations under the hood, that we have a special string type here, which does not need any memory kind of, but just points to the right place in the large memory. Awesome stuff, but gives us a little extra so that we need to convert it to the string which we expect. And on the other side, here's the pair part. I'm parsing the price of the taxi drive and parse this string into a float. yeah, I do this for every row and rows, and yeah, just for seeing our little data, I collect the first 10 examples. So I have a lot of ones and a couple of text drives where there have been 2 passengers and then how much they cost. And now I construct a group by aggregator with the histogram to get a feeling of how my costs actually distribute. I fit it, and yeah, let me fit it to everything. I also just fit it to the first part. And then as the final, I'm sorting them so that we have just 1 before 2, before 3, before 4 passengers. And yeah, then I plot everything together, and yeah, let's see what we get. Okay, see you, Simon. Thank you for being there. Have a good evening. Okay, so I've increased it to the full size of everything, so it's probably taking a bit longer than I was brave. Yeah. Okay, so what I use here is really just standard Julia plotting tools. So I construct an array of my subplots. Yeah, this is just an histogram for each different grouped by key. Yeah, I grab the histogram by getting it from this inner value, and then I have all these plots and just plot them together. So this is standard Julia version of creating a multiplot. And then adding a couple of options. So this link all is really nice so that all the Y and X axis are actually shared. I turn off the legend, just this tracks. I turn off the Y ticks. That a little bit the font size was a bit too large for my feeling, and add them an overall plot title. Okay, now I was a bit too brave. This takes longer than thought. Okay, 5 gigabytes. Okay. It will be ready. So I just continue with the next part of this streaming and big data. As always, please, if you have questions, just raise them. Okay, so the next part is about just big data, where you would also need to use multiple machines. And this is kind of a different use case. So in streaming, you will always have the luxury that your local operations is so small that you can indeed be on one machine. It just takes a bit longer then, but sometimes you don't care, but it's safe, it will work. But in certain cases, yeah, you have rather this big data case where you want to work in the throughput optimized way, that you're really quick and computing operations on very large data, so you need multiple machines. Okay, so now my plot is there. It took a bit longer than I expected for all the data, but it's safe, so that's a nice thing about it. And we see here now our summary. The sorting is by string, so we have a little bit surprising, unfortunate sorting, but okay. Yeah, so the passengers with 1 have the most amounts of data. Yeah, so we see that this is really the thing, and we have like a peak here at 6.5. I think the numbers are US dollar. And for passenger 2, we have the next most data, then 3, and then actually 5 looks like we have more data, and 4. Yeah, and as you know from your own taxi drive experience, it doesn't matter so much how many people you are, it just costs the same. And yeah, it probably gets a bit larger for the 6. Yeah. Okay, so this is a nice overview, and you can construct these easily with OnlineStats. So I hope this final example of this streaming data gives you also feeling, okay, even for these large data sets with OnlineStats, I would be safe. I can construct all my visualizations without fearing that my laptop is going to crash. It's really the benefit, one of the core benefits. It's also nice that there are all of these features already, but the key thing is that the algorithms are O of 1 in memory, so that nothing is ever going to explode. Okay, so then to the distributed setting. This is like a little setup. I run this now, actually. So with the standard Julia distributed, we can call the add processes function to pimp our current process with a couple of extra processes, and then run in all the processes something we want to use. In this case, we want to use OnlineStats everywhere. And just to see that we actually have pimped up our process, I call the number of processes functions and see that I have now 3 processes. So the one we already had plus the 2 we just added. This actually is mutating the state. So if I rerun this, I would get 5 in total. So but 3 is enough for this little example to see that it actually works. Okay, this is super large here. I make it a bit smaller. So these are now the 2 different ways of computing the aggregations. And as we have one-by-one semantics, we can easily parallelize this out. So this is really just an alternative benefit of having this streaming setup, that we can easily go big data. So on the right side, we have the sequential part where we do everything one by one after another. But because of our core step is really just doing it one by one, we can of course do it on the left side, that we have a machine or 3 machines here, which each compute their own aggregator, their own stat, and they then get merged into the final. So here we see also the 2 basic functions we saw at the very beginning. So we have this fit function, which is more or less the only thing you need in the sequential setup. And in the big data setup, you need in addition 1 second operator. Next to the fit, you need the merge. And this is everything you need. Then you're already big data ready. Yep, so let's take a look what this means in code. This is a nice little one-by-one example, how the parallel version would work, but it's not really parallel. So we just have kind of 3 different random inputs. Yeah, we have 3 different aggregators, 3 different stats. We fit them all to the separate inputs and then merge them one after another. So this is what's going to happen. But of course, this dummy representation is on 1 single machine. So in order to do it parallel, we can use the distributed macro. And I have another benchmark macro around, but let's take this away. Again, zoom a bit more into it. So this is the parallel implementation. I hope I haven't lost you. Maybe I was a bit too quick. Let's make this both on the screen. So this is what we do. We have 3 inputs. We have 3 aggregators. We fit them and merge them together. And this we can write in a very, very concise way using the distributed macro, which gets a merge function. So this is really the standard. This merge just has to take 2 arguments and output 1. So this is perfect. Our merge does that. And then we write a for function, which will get rewritten in such a way that it will run on different machines. But for us, it just looks like a for function. And each, what we do in every single run needs to be now this independent bit, which then gets merged. So we construct a new stat, a new aggregator here in every single loop, which is then put kind of to different machines. And we fit it on a new random sample. So in real life, you would have your subset on which you're currently computing. And then all these return values, so the last part of the for loop is then what is going to be returned from the machine, they get merged and aggregated in the central process. So yeah, and we get back our series like we would have computed it on 1 machine. That's really nice and scales to many, many machines. So this is core bounds, and yeah, you can use this to scale out massively. So I'm adding the B time on top, the benchmarking time, to get a feeling how fast this is. Yeah, and now I would like to compare with you the actual that we actually get a benefit. So because I'm now doing this not on Binder but on my local machine, we can actually see something. So on Binder, the benefit would be not that large. So let's make I write this down. So if we do this locally, we have, remember, I just scroll up. We have this case where we only have one single stat, and we fit every data, all data to it. So I just rewrite this. I construct my aggregator in front. I have the for loop and fit my aggregator kind of to all these different instances of random data. So and running this, I get kind of another timing, which for this very simple case is very similar. So it should be a bit more, and it is, yeah. And we see kind of 3.8 milliseconds and 3 milliseconds, not much, actually a lot more allocations, not sure where this comes from. So what I just want to showcase you is that if we increase this a little bit now to 15, for example, I increase the very same number so that we have the same amount of random data, we really see a time benefit. Okay, thanks for the frozen part. Thank you very much, Steph. There's another question. Just seeing from Vikas. Thank you. Does distributed create separate processes, or is it simply multi-threading with shared memory? It's an awesome question. Thank you very much, Vikas. Distributed really creates separate processes. So for distributed, it doesn't matter whether they are on the same machine or not. They could actually be in a connected network. Yeah, of course, if they're on the same machine, you can use shared memory. There's some speed ups, but in principle, the distributed setting, which we use here with the merge, this works really for even completely separated machines. And then even in my case now, I've 3 completely separate Julia instances running. Thank you for the question. And you can also do similar things with threads. There's extra support also for threads. I haven't included it here today, but it's supported. You can also see it in the documentation. Yeah, it's the same idea that you can with the one-by-one online solution. This can be super included into distributed computing. Okay, so I just spawned this to 15. I'm not sure whether my my screen is again back. So yeah, with this 15 iterations, yeah, I get a speed up of 2 on my system, which is already nice to see with this very, very simple setup. Thanks a lot, Matthias, for the feedback. So I have the distributed version taking 11 milliseconds and the sequential version taking 20 milliseconds. So this is quite something. And even, yeah, the allocations, I guess they are a little bit, yeah, I'm not sure how to interpret them actually. So whether the allocations are hidden in the other processes and just get not counted by this benchmark here. That might be the reason, because the data needs to be seen in all cases. So I think the allocations is a little bit misleading here, but the timing is not, because yeah, if the final process comes back, really everything is done. Yeah, so this is nice to see that you can use this seamlessly in this distributed setting because you have this merge operation, and yeah, and it makes it very, very simple. Okay, so we already are hitting the 8 p.m. mark. I always like to finish around 8 p.m. So I hope you got a feeling of the distributed setting, that this is really the key benefit of online stats and streaming analytics, that they just can be used everywhere, and they're so simple from their basic API that they are also performant from this starting point. So that's a lovely flexible utility which you should take into your toolbox. So the last part is about machine learning, and I just need to glimpse over it. And this is more about a feature-rich package. So that OnlineStats just has really a lot of things. So I'm just going a bit over this, saying to you what's all there. So what I really like, one simple statistical part is the bootstrap aggregator. So you can put a bootstrap around whatever you want. And what it will give you is a confidence interval on this estimator. That's a nice statistical thing. So you can take a look at the Wikipedia link, bootstrapping. And yeah, so it's a trick to get a confidence interval information out of nothing, kind of. That's the reason why it's called bootstrap. You create something out of nothing. It's really where it comes from. But it's powerful and many practical applications indeed useful. So this confidence interval has valid information into it, and it works by resampling the available data. But take a look at the Wikipedia article, it's really nice. What OnlineStats gives you is a super simple way to just apply this bootstrapping to whatever estimator you have. So yeah, if you want to get kind of a certainty measure, this is the way to go. This is super simple and yeah, statistically also valid. You can apply this, of course, to everything. There's time series support a little bit, so the auto covariance, where you can look how the current state is similar to the state before. So this is the same state, this is the state before, this is the state before that one, and kind of looking more and more into the parsed. So this is here kind of a typical case where it's similar. The reason is we use some data. So there's really the similarity, because we always just add a little bit on top of something big. So this is the reason why we see this typical scene here. So there's autocovariance and autocorrelation. It's a little typo of mine to not have both next to each other. Okay, it's not nice. Yeah, so there's support for this time series, standard time series information. For unsupervised learning, we can fit a covariance matrix. Thanks, Matthias, also for the comment. Yeah, I like this bootstrap part. It's just amazing how funny mathematicians are sometimes. Yeah, so that's the covariance matrix. Just an important part you see with the fit. Here's then each row. So we fit multi-dimensional data, but the OnlineStats always gets one by one, because a matrix kind of can either be seen by column or by row. We need to name this explicitly. This is just a fancy syntax with a pipe operation for just calling this function, and it will construct an iterator which looks over this matrix row by row. So this is just a nice side mark. So we can plot this and have a covariance matrix simply aggregated. The k-means is there, which gets us the clusters. And what's also really nice, it's a little bit more advanced. We have an online version of a principal components analysis. So this is also lovely just to know. There's a bit extra support for it, some extra functions to get things into your principal components. And yeah, we can again get the eigenvectors. So the principal components, they are learned. And there's also a little extra function here, which shows us how important these principal components are, namely by how much variance they explain. So this is maybe the most intuitive value. So the first eigenvalues explains really a lot of our data. And it's awesome that this is possible in an online matter. So yeah, it scales, streaming scales to big data. So I think this is the most advanced algorithm which you find in OnlineStats, and very helpful. On the supervised side, there's a standard linear regression. So if we have data which is kind of some data, and we combine all these values, this is matrix operations. So we have a couple of columns and we combine them. The first column is weighted 1, the second 2, and so forth, and then add them all up. There's plus some noise. With linear regression, we can get back these parameters. And yeah, and just having them fit, we see indeed there's here 1, 2, 3, 4, 5. So these are just these parameters here. Just a super short one for linear regression. We can use a predict function, coefficients function we had here. Predict is then for new data. We have also trees and forests which are there and online. So yeah, with constant memory, it's also nice to see. And they also have the classify method. And the final basic algorithm is the naive Bayes, which is the only one which has also super awesome plot support. Hopefully the others, especially the forests, gets also plot support somewhere in the future. But here we see, the naive Bayes is the probabilistic model, simple probabilistic model, typically used for classification. So the standard part is, or standard application is spam filter, so to say whether something is spam or not. Their naive Bayes classifiers are used quite a lot. And they work too. And the last little exercise I had here for you is to just try out classify and predict on this naive Bayes classifier as well. Okay, so there's one part left. There's a so-called start-learn aggregator, which is like a fancy linear regression. So you can go do quite a lot more, but it's also a little bit more complex. So if you like to know a bit more about what's possible here with advanced linear regression, yeah, take a look at the documentation. It's nice to see that. So yeah, maybe to summarize it, that's a set of a little framework to do stochastic approximations. For me, it showcased definitely also this passion to get in the machine learning part and also more advanced models. Okay, so this was it from my side. Let me summarize again. So we went over online stats and we've seen kind of a lot of things. I just make a quick one. So we had a couple of basics. The simplest one was that we have a fit function where we go step by step. We have our aggregator, our so-called stat, our online stat, and we just fit it to the next data point and take the next data point and fit it again and mutate our internal state correctly. So this is the way everything works. And in addition to this fit function, we also have this merge function where we can combine two aggregators together. That was basics 1. So this is really the core interface of all of this. And you can imagine this is so simple, you can easily extend it. The second basics was then about some groupings, how to combine different aggregators and also how to do filtering and transformations. We had about the weights. Then we've seen just a couple of examples from the visualizations that OnlineStats already comes with a lot of features included to visualize your data in an efficient manner. And this OnlineStats is especially suited for visualizations because you always want to see kind of all your data at once, but they don't fit into memory. This is just, as soon as it gets a bit too big, they will never fit into memory. So having these aggregations is the way to go, so that arbitrarily large data can be seen at once in the sense. And this is really a key feature. Then I've shown you kind of the concrete streaming and distributed the big data applications, how they would be implemented in Julia, and that there's also an awesome support for the streaming part. Okay, and then the last example was about the machine learning, which is just nice fancy stuff, batteries included, that you can use these mathematical models right away, that they are supported with OnlineStats. In principle, you can also build your own, but it's always nice to have the package come with some standards. So trees are definitely standards and linear regression as well, but we've seen a bit more. So the online PCA, I really like this, that it's available. So check it out. Okay, nice. So then I want to thank you again. We are still at 9 people. Thank you for staying with me and also for the questions. Meanwhile, for your support. I'm sorry for the breakdown of binder here and there. And I hope we could still make the session informative for you, that you got to know OnlineStats lost your fear of it if you had it, and then see how simple it is to apply these algorithms to streaming data. Thank you for your comments. I'm very glad. Thanks, Steph, also for saying it was good to follow. That's the purpose of the series, and I'm happy that it works out. And also for myself, I like to summarize the information, get also the parts, how you may apply this to real life. This is something I value a lot. So you've seen these CSV parts and the distributed, because for me, it's personally important that you see, okay, this also works with a bit more realistic data. And actually there it shines. Nice. Thank you a lot. I will also take a look on the binder part, whether this is going to be something we have to deal with for the future. Then, of course, I will simplify also the local setup so that people can easier spawn their local Jupyter notebook. Yeah, that's definitely something to consider. Or I will see whether there are also other options next to binder, but so far binder was the most stable solution. Yeah, we'll see. Okay, so if you have some more questions, please feel free to ask. I'm still here and happy to be of help. Okay, great. I'm stopping recording then.